All right, everybody, welcome to our afternoon session of streaming live OpenSpace to YouTube as part of the Lunar and Planetary Science Conference. As I've stated in a couple of the sessions earlier this week, we have some guest speakers today for doing our presentation. First, we have KaChun Yu. KaChun is the curator of space science with the Denver Museum of Nature and Science, and he'll be driving OpenSpace for us today. And also with us is Bob Reynolds, a research associate at Denver Museum of Nature and Science. And Bob will be narrating and kind of storytelling for us today. So with that, I'm not going to hold us up too much longer. I'm going to turn the floor over to Bob and KaChun, and we'll get this off the ground. Please keep in mind, if any of you guys have questions about what you're seeing, feel free to send them in the chat for the LPSC conference or on the chat for YouTube Live, and we'll try to answer those questions as we go through. Additionally, if you have anywhere you would like to visit, please let us know, and if it's something we can accommodate, we'll do our best to do so. And I will go ahead and turn the floor over to Bob and KaChun. So thank you, Bob and KaChun, for joining us today. The floor is yours.
Great. Well, thank you, Adam, very much for inviting us to this program. And I'll let KaChun just introduce himself quickly, because KaChun's going to be flying, and I'll be pontificating. So, KaChun, why don't you just quickly hop in and introduce yourself?
So I'm KaChun Yu. I'm an astronomer at the Denver Museum of Nature and Science, and I use the OpenSpace software along with Bob to give presentations to the public about our planet Earth in our planetarium and now online. And since we don't have that much time, I'm going to turn it back over to Bob.
Great. Okay, well, thanks, KaChun. So we're going to be using OpenSpace as a vehicle to examine features on Earth. And this is a program, it's a little vignette of something that we do at the Denver Museum of Nature and Science. We've been doing it for quite a few years now. We call it Digital Earth, and we're now actually doing a program for grade schools that we call Digital Earth Academy. And we use OpenSpace as a way to teach geography. And we do topical programming. We do everything from exploration, mountains, volcanoes, earthquakes. You can sort of imagine the span of features. We're going to give you an example this afternoon of a program that we put together a month or two ago on ice. And we're going to be talking about ice as an agent of erosion and ice as a recorder of climate. So two different themes of ice. And we're going to just give you some vignettes. And do ask any kind of questions that might come up. I'm unfamiliar with your backgrounds and perspectives, so if there's something that I haven't covered or that I should amplify, please let me know. And I'm a geologist, so I'm sort of speaking to you from the standpoint of rocks. I'm a soft rock geologist. I study sedimentary rocks, and I'm really a stratigrapher, so I'm a little bit out of my field in glaciology, but bear with us, and we'll be giving you a tour, and hopefully it'll be amusing and of interest. We're starting out in Alaska. And as we talk about ice, we discussed the fact that the Earth is a water planet. The vast majority of the water is in the oceans and is unavailable. And the surface water that is fresh and potentially drinkable, 2/3 of it's actually frozen as ice. And so ice is an important component of our water system. And we're looking here at the Malaskina Glacier in Alaska, southeastern Alaska. And the Malaspina is an interesting feature. It's a Piedmont glacier. It comes out of it's actually the Seward Glacier that's coming out of the mountains there, and the Agassiz Glacier is up to the left, to the northwest. But the Seward Glacier feeds out onto the flats, effectively at sea level. And it's a wonderful visual of ice. Ice deformation is seen from space and seen from above. And some of you might have visited this spot, but it's a very compelling graphic, and so we use it to show people white ice and the black material, which is really ground up bedrock being carried by the glacier. And here you'll see actually an animation put together by NASA just illustrating change through time, and KaChun is just running the sequence a few times here so you can actually get a feeling of the glacier flowing. I mean, it's moving through time, and you can see the change in character year by year. This is I can't see the pages there, but this is about an 8 or 10 year time sequence here running again. So that's the Malaspina Glacier, and we're going to back up and
yes.
they're coming together, and the black lines again are moraines, and the moraines are lateral moraines on the sides of glaciers. They're medial moraines where two lateral moraines come together, and you'll see some black objects. I want you to see the black objects that are going down the glacier. I want you to think about what those might be, and we're going to have a chance to look at more detail at these glaciers, but here you're seeing them move through time, and again you're looking at about a 20 or so odd year sequence. You can see it better than I do. The black bands or ribbons on the glaciers are what I wanted to ask you about.
I don't know how.
And the very prominent black bands are, you might have already guessed it, but of a black band, and then these annual ogives illustrate the annual cycle or pulsing of the glacier as it's moving down the mountains. So wonderful records here of glacial features in Alaska, and these glaciers are dynamic. They're changing every year. Obviously they're flowing, but as you can all well imagine, they're also melting, they're retreating, and we're going to nip down by Juneau, the capital of the state of Alaska, which is, some of you might have been there, a relatively inaccessible place. You either approach it by land, by water, or by air, and Juneau is fairly isolated, but it's very nicely sheltered in the inland passage here. It's sheltered from the storms of the Pacific by a whole series of islands, and here's Juneau sort of tucked in. You can see its airport coming into view, and then just behind Juneau is the Mendenhall Glacier, which is a very accessible. If you're in Juneau, you hop in a cab and you go out there and eyeball it. There's a couple vantage points that people head out there to look at the Mendenhall Glacier, and it's one of these situations where, because of the retreat of the ice or the glacier, it's actually getting difficult to see it from some of the vantage points because it's heading out around the corner, and we're going to zoom in a little bit here, and then we're going to borrow some imagery from James Baylog. Some of you might know him. He's had a program called Extreme Ice. He's created a series of movies and videos documenting changes in ice on the Earth's surface over time, and here you're looking right up the Mendenhall Glacier using OpenSpace, but we're going to get ourselves into a position here and then switch over to a ground-based camera that James Baylog and his Extreme Ice team have been monitoring, and you'll see here changes over a 10-year period in that Mendenhall Glacier. And this is typical of the work that James and his team have put together, looking at a variety of glaciers around the world. You'll see this video will cycle, but the key thing to appreciate is not only is the glacier retreating, but it's also losing mass. It's losing its volume. So the toe of the glacier is backing up the valley, and it's also shrinking. So in common with all of the world's glaciers, the ice is melting, associated with the warming of the Earth's atmosphere and waters. So it's an illustration of global change. And that's what it's going to bring us to our second theme, the first being that glaciers are dynamic, they're moving, they carve the Earth. Again, you can see the moraines as testament to the carving. And the glacial valleys are very diagnostic with their U-shaped valleys. valley, U-shaped configurations, and so we're quite familiar, those of us who live in areas that have been glaciated, with the power of ice to shape and modify the world. We're going to use OpenSpace to cross Canada, and we're crossing over the top of the Canadian Shield here, heading across Nunavut and towards Greenland. And Greenland is a wonderful reservoir of ice. There's on the order of 7 meters of sea level stockpiled in the ice on Greenland, and we're going to use a couple of different tools to look at the ice on Greenland. If we look at it from a little bit of distance, you see a big ice cap, and we're all basically familiar with the lay of the land. The ice is on the order of 3,000 meters thick. It's the bottom of the ice in the central part of Greenland is actually below sea level. It's depressed the whole landmass of the Greenland island below sea level in the central part, and that ice is slowly melting, in some cases more rapidly. But let's see if we can, we'll use a video here and see if we can zoom in to Greenland and make the ice translucent by using radar imagery. So again, we're relying on NASA technology, and here we've got a visualization of an aircraft flying across. The National Snow and Ice Data Center has been involved with this. NOAA has been involved with this. Large American government efforts. But you'll see, you can actually see into the ice, reflectors indicating episodes of melting, and you can calibrate it using that ice core. And then we've flown many sorties over the island of Greenland, and so we've built a three-dimensional model of it. In fact, KaChun, what we might do is, once this thing finishes, why don't we run it a second time, just so that we can see that first cross-section nicely. Here you can see the ice is color-coded by its age, with the youngest ice on top being the green, the Holocene ice, and the middle ice being a little bit older, the last ice age really. And then at the very bottom, squished down in there, is some ice left over from the previous ice age, we call it the Eemian. And it's not omnipresent underneath the ice in Greenland. It's sort of a little patch up there. But I think we'll strip it back down. So we'll take away the ice from the last ice age here, and you'll see the Eemian ice hiding underneath. And this video, to me, is extremely compelling. And I wanted to re-show, maybe it's just KaChun, I don't know if you can just show the first part again.
Yeah, I might be able to, I think we have a still from the video that
okay, but that would be really good if we just showed the still from because that's the killer image, is that cross-sectional view from the radar data, and we can, if we can see it with the ice core on it, I'll just comment on it.
Yeah, so I'll turn off the video and I'll switch over to
yeah, sweet. So this was this. Let's see. That basically is it. But it's really the one that's got the stripes on it. There's that one. That's perfect. So right here. So this is one of these killer images. I mean, I'm a stratigrapher and I studied layered sedimentary rocks, but this view warmed the cockles of my heart, as I hope it does yours, because here you're seeing reflectors, and this is radar data obtained from an airplane. So they're bouncing radar waves off the internal layers in the ice and then off the bottom of the ice. But then they've calibrated it with one of these cores. And there's a series of cores in Greenland that go all the way to the bottom. And this one, it allows you to see which reflector is which age. And they've had students, as many of you probably know, counting the layers. We'll see that in a second. But you can count the layers down, and they get a little bit smudgy at the bottom because the ice flows. But you can see, I think I'm trying to read those numbers, but it's 2,000 and 4,000 and 7,000 and then 90,000 down towards the bottom. So you can see that we have a very robust understanding of the morphology and the characteristics of the Greenland ice sheet based on coring and radar data. A wonderful combination. And what does that tell us? We can back out now. KaChun, let's run that other video, and we'll just remind people about ice coring. And there's been lots of ice coring operations in Greenland and elsewhere in the world. And of course, it involves substantial machinery, and you're running a tube down into the bottom of the ice ice and you're collecting ice core samples, if you look at them closely, you'll see the layers that represent the annual cycles. There's a summertime, wintertime phenomenon. And workers in the lab, we've got some views here of Lonnie Thompson's lab at the University of Ohio. And Lonnie's been working on mountain glaciers, and he stores his cores just as we do here in Denver. We've got a facility just like this in Lakewood at minus 40 Fahrenheit, which interestingly is minus 40 centigrade. And the ice cores are sampled. The little air bubbles represent fossil air. And so we have used the ice as a recorder of climate. You can see the annual cycles here. This is from the Greenland ice core. And students count those layers down, and we get the bubbles. The little bubbles in there contain fossilized air, and we can see the composition of the air back through time. And it's an absolutely wonderful, wonderful record. We've got it from Greenland, we've got it from Antarctica, we've got it from the ice caps on tops of mountains. And resonate and reinforce one another. Thinking about the changes through time, I think we've got some. We will illustrate the. This is the Greenland ice mass, and we're using the GRACE satellite paired system here to look at the gravitational attraction. You're familiar with the pair of satellites that are flying along, calibrating their separation. Increased mass beneath them will draw them. Let's see, the first one will move a little bit faster. I guess so they separate out a little bit if there's increased mass. In any case, mass can be measured very carefully by these two satellites. And here you're seeing, in terms of trillions of metric tons, the loss of ice from Greenland. And that represents on the order of 50 cubic miles per year of 50 cubic miles per year of melting, and steady diminution of ice on land in Greenland. And of course that ice is going into the oceans, and you have a corresponding sea level change associated with melting ice on land. And sea level rise is increasing. It's a little bit north of 3 millimeters per year right now. It's a combination of the thermal expansion of the water and the melting of ice that's on the surface of the land. But together, those two phenomenon, plus a teensy little bit of groundwater that's being extracted and put into the oceans, is yielding this sea level rise curve, which of course is now very carefully calibrated based on radar data from satellites. So we've got an early record in pale blue that would come from a stick stuck in the beach, a tide gauge, and then in the 70s and onwards, we've got data coming from NASA's fleet of orbiting satellites that are looking down at the sea surface. And of course, this is a challenge for us as a civilization because we've got a huge amount of our infrastructure is located at or near sea level, and as sea level is rising, it's a global challenge for everybody to recognize the need to modify our infrastructure. And of course, this all ties back. Let's see if we might admire a glacier here or two, but then I'm going to bring up the Keeling curve, or a modified version of it. Here, this curve really is our last graph, and it's just a reminder that the data that are coming from the ice core in different parts of the world corroborate each other, whether it's from the South Pole or from Greenland or elsewhere. And you'll recognize the familiar carbon dioxide curve on the top, and there's a methane curve there on the bottom. And these again are coming from bubbles in the ice, and they've been tied to David Keeling's curve from Mauna Loa in Hawaii, which is of course replicated in many different places around the world, to the point where we call it the Keeling curve. And he gave us the atmospheric measurements of particularly carbon dioxide, which are now widely recognized. And of course it's a symbol of our combustion of fossil fuels, both coal, oil, and natural gas, in which we're taking sunlight from ancient times and putting that energy and that carbon into the atmosphere, and consequently modifying the atmospheric composition, leading to the change in the greenhouse phenomenon associated, of course, with global climate change, which we're witnessing today. And so we can back out a little bit, and we can use our remaining couple minutes. We might look a little bit more at Greenland, and then we could wander over to Iceland. these are there's wonderful glaciers coming off of Greenland, but most of the Greenland island is actually a big mass of ice that doesn't have very many glacial outlets. There are limited numbers of places where that ice is coming out into the ocean, but it does spawn icebergs, and it's fairly, of course, a significant contributor to sea level rise. If we look at Iceland, Iceland is greener than Greenland, and the ice caps in Iceland are on volcanic highlands, and of course there's a whole series of volcanoes underneath the ice, and there's a wonderful variety of these volcanoes, and they periodically erupt under the ice, and they create giant floods that come out under these big floodplains called Jökulhlaups, and a little bubble of water will come underneath the ice and come galloping down across these big strand fields and wipe everything out. So there's not much infrastructure built on these things because they periodically get demolished. You'll also see black lines in the ice here in Iceland, and some of those, of course, are moraines like we saw in Alaska. But there's other black lines that go across the feature, and these are not landslides. These are actually ash deposits. So you've got volcanic ash, which is dark color. Iceland, of course, is basaltic magmas and basaltic cinders. So you get alternations here of moraines plus basaltic ash that falls out on the ice in Iceland. And there was a famous eruption just a few years ago, and the Mount E eruption. And I hadn't realized we'd quite get to this far in the presentation. So the question about how you pronounce that Mount E is something that troubles many of us. And Icelandic people are not troubled by it at all because it's a concatenation of something like mountain and volcano and glacier. And so for them, they're just putting together three different words. For us, it's a complicated word that Elgin, Fetkin, Yomkin, something like that. And I talked to somebody who said, well, if you can't remember how to say the word, you say something to the effect of oh, I forgot the yogurt. And you've got something close to the name of that mountain, which erupted about 10 years ago and caused a lot of consternation. You'll remember perhaps that there was clouds of ash in the air that restricted air traffic coming out of Europe, and KaChun was amongst those people who were stranded in Europe because of the air traffic, because of that glacier. We just saw the Vestmannaeyjar Islands there. Well, here, this must be Mount E right here. You can see the actually pair of images there. The one on the right has the ash on the ice, and the one on the left has no ash on the ice. So presumably the one on the left is pre-eruption, one on the right is post-eruption, and you can see the dramatic variation. One last story we can tell KaChun if we go to the Vestmannaeyjar Islands, which are just to the south off the screen, right there, just coming into view. Many of you will be familiar with Surtsey, which is the little island on the bottom. And if you travel here, it's not really easy to get to Surtsey. In fact, I don't think you can go there unless you have a research permit of some kind. But if you go to the Vestmannaeyjar Islands, there's a port city, and some of you will remember the volcanic eruption here that threatened to close the harbor of the city. But here's Surtsey in the lower center part of the screen, and up on the Vestmannaeyjar Islands, if you travel there, you can take a ferry from the mainland, and wonderful community. This is where puffins live, and there's some issue about the herring supply, and the puffin supply follows the herring, and there's not as many puffins as there used to be, but long stories there. But this the volcano that erupted on this island threatened to close the harbor on the northern end of that island. You can see it was almost, the flow was coming down it was coming into the water, and the fear was that it would close off the harbor, which is of course the lifeblood of the island. And this is a place where they use fire hoses and water from the ocean to try to cool the lava. They effectively did cool the lava. Whether it was actually whether they stopped or modified the lava flow or not is not quite clear, but heroic efforts were undertaken to save this harbor. And it's a wonderful place to visit today. Well, a last story about Surtsey. When they first got there, it's of course a treasure because it emerged from the ocean. Many of you will remember that, and so it started out as a blank slate, and people were very interested in how biology would colonize Surtsey, and there's a very elaborate analysis of the first spider and the first snail and the first albatross, et cetera, to come to Surtsey. But the first geologists that got there came and saw, of course, a cinder cone, and to their astonishment, they found granite pebbles. And the granite pebbles of Surtsey were quite a mystery to people. And I'll let you ponder a minute how there could be granite pebbles in Surtsey. And while you're pondering that, KaChun, if we do have that last video of the polar sea ice, I'll let you guys look at this flow. Here you can see the date on the top of the screen. And so you'll see we're running from the 80s probably up until the aughts. And you'll see the ice is color-coded with the thickest ice being in white, and the older ice and the thinner ice being in blues. And you'll see that we come up into the 90s here, and ice is flowing around Greenland. Here we're coming up to the 2000s, and the ice amount the ice cover is diminishing, but what's more important and interesting is that the older ice is diminishing. So the ice cover, which we all talk about, is diminishing, but the amount of ice that's older or thicker is diminishing as well. So as we lose the polar ice cap, we're losing it not only in terms of aerial coverage, but also in terms of the thickness of that ice cover. So as it now we just flip back to the 80s, so the scene is now, we'll run it all the way up again. So we're going from about 85 to 2010 or something. And you'll see that the amount of white, which is the thick multi-year ice, is going to diminish as we go forward. And of course, the aerial coverage is diminishing as well. So there's sort of a double whammy going on there. But I want to come back to the question of the granite pebbles on Surtsey. And I can all hear you waiting with bated breath to announce how they got there, but this is a clue. Remember where Surtsey is, and watch this polar ice flowing down across the edge of Greenland, which of course has lots of Precambrian basement in it. And some of you will have gotten the answer. I can't really see it in the chat room very well. You're not chatting enough. I don't know. It could be you don't have access to your chats. But in any case, the pebbles that the volcano brought up on the cinder cone that burst forth from the ocean floor back, I don't know, probably 45 years ago now. But those pebbles were ice-dropped granite pebbles that had come by glacial iceberg and had fallen on the floor of the North Atlantic. And then as the volcano erupted, of course, it brought everything it could find up with it, including the drop stones. So there's drop stones from Greenland on the beaches of Surtsey, and they got there by ice flowing, as you're seeing in this image here. So that brings us to about 3 o'clock, and I gather we've got sort of a soft close here, so if people do have any questions you'd like to ask of myself or of KaChun, we'd be pleased to try to answer them, and we hope you've enjoyed our little tour.
Well, Bob, I do want to let you know, just as you gave the answer, because we have about a 30 to 45 second lag on the stream, Hunter actually submitted his guess of drop stones and was correct.
Congratulations, Hunter. That's wonderful. Yes, indeed.
So with that, I am going to thank both KaChun and Bob for joining us today. We appreciate it very, very much. They have a couple of new programs, the Digital Earth. Is that correct, KaChun?
Yep, we have a bi-monthly Digital Earth program that goes out at 7 p.m. So you can check the Denver Museum of Nature and Sciences website for the details for our next one, which I think is in May.
Excellent.
And then we also have a Digital Earth Academy, as Bob mentioned, which is a school program. And so we've been broadcasting to about 2,000 students each month. And there's both those programs. The Academy program is free, but you have to sign up, and so you can see what we do for kids, for school children using the software.
Excellent. Well, with that being said, again, thank you guys for joining us today. Those of you that have joined us from LPSC, we will be continuing to do streams throughout the rest of the week. You can check our schedule by visiting our booth in the exhibit hall. There's a link to the schedule there. And for those of you that found interests in today's presentation, feel free to check out the Denver Museum of Nature and Science website to see when their Digital Earth programs are there. Before we finish up, I do have a question from Hunter, and it says, are these radar profiles available in OpenSpace or Digital Earth? Is there a way that they can get these profiles?
I think the answer is no. The video that you saw was actually something that was produced through, I think, NASA's Science Visualization Studio. So we were able to take the video and using WorldViewer, another program that the Elumenati has created, along with OpenSpace. We've been running both video as well as static slide assets, different media assets. So unfortunately, neither Bob nor I have had access to those data sets.
Okay.
You might have to contact the SVS people to find out where they got their data from.
All right, and Hunter, I did chat you my email address as well, so feel free to reach out to me, and I'd be happy to connect you with folks that might be able to help you find that answer. And of course, that feature was enabled through the power of WorldViewer, which is our content management system for our immersive systems for the Elumenati, which the Denver Museum does use in order to accommodate or accomplish some of these data sets in conjunction rather with OpenSpace. So you can reach out to us and we'd be happy to help you be able to enable that feature as well. So again, guys, thanks. I'm going to go ahead and wrap up, and I look forward to joining the next Digital Earth presentation.
Thanks a lot, Adam.
All right.
Thank you, guys.
Yep.
Thanks, everyone.